All right. Hi, everyone. Welcome to, the RChain DevCon, first RChain DevCon, and to my talk about the correct by construction Casper protocols and their protocol states. Should be a pretty interesting talk, but pretty action-packed, so I'm going to get started. We have this is like this kind of outline while I try to get my screen replicated across both of my laptops here. There we go. So we're going to do an introduction to consensus, just basic definitions that consensus protocols have to satisfy. Talk about the safety proof, which the protocol states satisfy. And we're going to try to give a proof of FLP impossibility for all of the consensus protocols that satisfy this, that have these protocol states and these protocol state transitions. So let's get to it. So consensus protocols are basically about nodes in a distributed system making decisions in a consistent way, even though they could be making mutually exclusive or inconsistent decisions. For consensus on a bit, we might want to all decide on the same bit and not have some of us decide on different bits. And we can also decide on interesting values, not just for bits. And we could even decide on values for a row calc virtual machine. Knock on wood. I'm just trolling. It is almost for sure possible. I just don't know that anyone has completely done it yet. But we can decide. I think we've done a blockchain and a sharded blockchain to some extent. Consensus protocols, normally we want them to have safety and liveness. Safety means that nodes make decisions on consistent values, whereas liveness means that nodes eventually make decisions. The way to think about the safety property is that if you just aggregate all of the decisions that all of the protocol following nodes have made, that all of those decisions should be consistent. They should be either on the same values or on values that are consistent, which is to say, like maybe in for example a sharding system, you might have nodes decide on different values, but in a way that they're all deciding on the same state. Even though they're not all deciding on all of the pieces of the same state. So still we can think about this property of safety kind of very broadly in terms of whether the decisions made by nodes are consistent. And liveness is basically a property that they will eventually make a decision after executing the protocol enough. And finally we have non-triviality. Non-triviality basically means that the outcome of the consensus protocol isn't something you can pre-compute from any point on the network. You have to actually do communications in order to make a decision. You can't just compute locally that we're all going to decide on 0 or 1, or it's not really a consensus protocol. So it has to be kind of non-deterministic in a sense. It's not locally determinable to be a consensus protocol. You have to be able to decide on 0 or 1 through an execution of the protocol as a function of your communication with other nodes. And that's kind of what this little drawing represents. So we should be able to get to 2 protocol states that are decided on mutually exclusive values from some initial protocol state that isn't decided. And that's kind of what the non-triviality is all about. It's all about these kind of bifurcations that where you choose between alternatives and can never go back. So consensus can be hard because in a distributed network, all sorts of stuff can happen. Messages can be delayed, reordered. They could be just not delivered. A protocol is called asynchronously safe if it's safe regardless of timing assumptions. Same thing for live. You can call it asynchronously live if it's safe regardless of timing assumptions. It's called Byzantine fault tolerant if it can tolerate nodes behaving arbitrarily. And so basically what we want out of consensus at the end of the day is to build asynchronously safe, Byzantine fault tolerant consensus protocols that make decisions on stuff that's relevant to our interests. Like, for example, the states of the row calc virtual machine. So now we're going to start talking about Casper specifically. We're going to try to satisfy these definitions and build protocols that kind of, in a correct by construction way, are derived to satisfy these definitions. So we're going to start with safety. We're going to have protocol states and protocol state transitions, how we're going to think about the protocol. And a protocol, the protocol describes how an individual node executes. So like I'm talking about the protocol states, meaning all the possible states of an individual node, and the transitions, meaning all the ways that an individual node can progress through the protocol. And we have like transitivity of protocol executions, where like, oh look, if I have and I draw a little arrow to denote the fact that there is a protocol execution from one state to another. And I have transitivity, which means that, oh, if there's a transition from A to B and B to C, then I can also find a transition from A to C. And we also have this thing called the estimator, which will relate our protocol states to values of the consensus, either by spitting out values or by spitting out propositions or like types that the values of the consensus should satisfy. And we can kind of handle both of these cases, and both of them provide kind of valuable intuition. But you can think about these properties of the consensus as being satisfied by sets of consensus values. So there's you might think about all the blockchains that have some block at some height as a set of blockchains, or as a property, has this block at this height. So the estimator will kind of, in the binary consensus, giving you an idea, will map every protocol state to a 0 or 1. In the blockchain consensus, it'll map it to some kind of fork choice rule. We have this kind of system of properties. Really, you can think of it as a type system for talking about the values of the consensus. So, a type system for talking about the blockchain, or in the bit, it's pretty simple. So we write that value of the consensus entails a property. If it satisfies it, or if it's in the set that is defined by that property. And we write. You can also write this from the estimator, whether the estimator is a property or itself just a protocol state. Sorry, just a value of the consensus. And now we have we're running into our first kind of really important definition here, which basically says that a property has this property called estimate safety if it's invariant in all future protocol states for the estimator. So if the estimator implies P, some property P for all future protocol states, then for the current state and all future protocol states, right? So the current state sigma and all states that sigma can transition to, then it's called safe. So it's called safe if really, in all states that your node can go to, single node can go to, then it's satisfied. So in this drawing here, we have a binary estimator on some random protocol described as states and transitions. And the ones in red are safe because all their future states have a 1 on them, whereas the ones in white or light blue here are not safe because they have 0s or 1s. So here is basically the core of the consensus safety proof. It's got 2 parts. Lemma 1 basically says that, if something is safe at sigma, it should be safe at any future state from sigma. It should be pretty intuitive because safety means that you hold for all future states, and transitivity meant that all your future states are themselves, the future states of future states are themselves future states. And so any future state of sigma prime is a future state of sigma. So anything that's going to be invariant for all of the sigma's features will also be invariant for all sigma prime's features. And so safety at sigma 1 down here will imply safety at sigma 3 up here. Backwards consistency is perhaps more interesting. If we have safety of P here, then that means that we didn't have safety on the negation of P somewhere downstream. So it's not the case that there exists some previous state that could have evolved to this state that is safe, that was safe on the negation, that other thing that's safe here. So basically, you could imagine that not P was safe at some previous state to sigma 3. Then not P would have to also be safe at sigma 3. But we've already kind of assumed that P is safe at sigma 3. And so lemma 2 basically is called backwards consistency, where basically like the previous states, all states causally before this particular state, or that might have been causally before this particular state, didn't make any decisions that are inconsistent with the things that are safe at the state. And so these two lemmas together let us know somehow that if sigma 1 and sigma 2 down here, sigma 1 and sigma 2 have a common future state sigma 3, that safe on P at sigma 1 implies not safe at not P at sigma 2, which means that like somehow sigma 2, as soon as you're safe at P at sigma 1, you know for sure that at sigma 2 you weren't safe on something inconsistent. So what the strategy of the proof here is going to be that if you decide on something only when it's invariant in all your future states, and you and I and I also do the same thing, but we have a common future state, meaning that we could both, our protocol could execute so that literally like the code and the state of our software reaches exactly the same state, then if we decide on those things that are invariant in all our future states, then we'll be deciding with consensus safety. We'll be deciding in a way that's consistent because we have a common future state that we could both progress to, which satisfies all of the invariants in each of our local states. And so this, and basically, well, I guess I just walked through this, so skip a little bit. And basically, this is exactly kind of equivalent to consensus safety because safety on P at sigma 1 implying not safety at not P at sigma 2 is kind of the same, dropping the implication and using De Morgan as not being safe on on P and not P at sigma 1 and sigma 2. So this basically is totally equivalent to saying that you can't decide inconsistent values for protocol states that share a common future state. So basically, but this safety property that I gave is a local property, as opposed to this distributed property that we kind of now have if we share a common future state with the other nodes in the network. That's kind of the thrust of the first proof, is basically that if we have a common future state, then we get to take advantage of this distributed consistency property to know that the things that are invariant in all of our future states are consistent. And then as long as the decisions that we make only correspond to these things that are safe, then we're going to make consistent decisions. And basically, we can make decisions on two things. We can make decisions on propositions, and we can make decisions on values. We can decide on a proposition if it's safe, and that means that we will no longer accept any like value of the consensus that doesn't satisfy that proposition. And we can decide on a value, which means that we're never going to decide on any propositions that aren't satisfied by that value. And all these decisions have to be covered by these invariants in order to maintain consensus safety through having common futures with the other nodes. So as long as we have a common future and we decide only on invariant stuff, then we can make consensus safe decisions. So that's part one of the proof. Part two of the proof is going to be a construction that guarantees that we have common future states. So, I've always been supposing that we have a common future state in this reasoning, and so I have to kind of provide that to you. And that's what part two is all about. And this is kind of where it gets interesting because we're not going to be blind to the internal structure of protocol states anymore. We're going to need to think about their relationship to something like, for example, something like communication. So we're going to guarantee this, though, as long as there's not so many Byzantine faults. If we have non-triviality, what that means is that there are going to be protocol states that are safe on mutually exclusive outcomes. And because these protocol state graphs represent the protocol states that individual nodes can go through, it's totally possible for a node to end up on the left or on the right. But if two nodes end up one on the left and one on the right, then there's been consensus failure. There's been a consensus safety failure because they've decided on inconsistent decisions. But non-triviality kind of means that it's possible to have consensus safety. We have these transitions to these protocol states that are deciding on mutually exclusive outcomes, and we are on a distributed network, and so we don't necessarily have a guarantee that we're going to transition through the same states. But still, we have to make sure that we don't end up in the same values, right? So we have to somehow coordinate. We can't independently follow the state transitions. We can't think of them only as state transitions of individual nodes. We need to understand them in the context of nodes receiving messages from nodes in common, right? Two nodes have to be receiving messages from senders that are not sending them messages completely independently for them to have a hope of coming to consensus in the context of non-triviality with safety. Because if you progress completely independently through the protocol, then you will very likely or very possibly decide on inconsistent values. And so instead, you need to follow a common signal. So what we're going to do is we're going to assume that some nodes are named and are consensus forming, and that receiving messages from these nodes is what a protocol state transition is. So we have nodes that are forming consensus, and somehow they're the ones that are meant to synchronize or cause or coordinate nodes through this protocol so that they don't make inconsistent decisions despite their opportunity to make inconsistent decisions. The opportunity that has to exist for the protocol to be non-trivial. So the state transition, the states will correspond to these sets of messages, but still those messages might be completely independent from each other for different nodes, and in which case they would decide completely independently and have consensus failure. And this behavior of having nodes who are following the nodes who are producing these messages behave completely independently can be captured through this notion of equivocation. Equivocation means running the protocol in such a way that can't be characterized by a single execution, but must have been through more than one execution. So imagine if a node is at the two green spots. That's potentially plausible that a named node, executing the protocol could hit both of those in a single protocol execution. However, on the red ones, there is no single protocol execution to go through both of those protocol states. And so a Byzantine node, what they're going to do in order to achieve this kind of independent transitions is they're going to run the protocol independent times, more than once, and not have a single execution trace to the protocol, but we'll have a forking or multi-branched execution trace. And these are called equivocating, and this is fundamentally going to be enough to cause consensus failure, because it's fundamentally the case that starting from the initial state of the protocol, you can end up in one outcome or another as a function of the messages received from these nodes, and if they send you messages completely independently than the messages they send me, then we can end up in different protocol states, just because of these equivocations. So equivocations are fundamentally enough to cause consensus safety failure. There's no way to design a consensus protocol that is going to survive 100% equivocation faults. But equivocation may be detectable. And as long as some of the nodes are not running these nodes independently, we might have a chance. If some subset of nodes are not equivocating and are not showing us independent message signals, we might have a chance of coordinating around the same decisions. So if less than some number of faults occur, then we can actually potentially make consensus safe decisions. how do we make sure that nodes have a common future state if there's less than some number of equivocations? That ends up being kind of our question. Remember, our goal here is to make sure that nodes have common future states. And we kind of showed that because of non-triviality, it's going to be possible if there's enough equivocations for them to not have a future state. So how do we make sure that as long as there's less than some number of Byzantine faults, we do have a future state in common? Well, what we're going to do is we're going to count equivocations. It's going to be our first step here. We're going to define equivocations and be able to measure them from our protocol states themselves. Specifically, first we're going to talk about our messages, and our messages are going to have. I already mentioned that they have a sender, so this label V, and then they have a protocol state. So a message says, "Look, I'm at this protocol state. Oh, I'm at that protocol state," and it should be that a validator who sends these messages only sends them from protocol states for which there exists a protocol execution through those states. Otherwise, that corresponds to equivocation. So we're going to use the protocol state and the label to detect equivocation. So here's kind of the definition of equivocation, right? It's a pair of messages which are not the same message, which have the same sender, but for which there isn't a protocol execution from one state to the other. So, if you pass me a set of messages and I can find a pair of messages inside them that satisfy this relationship, then the sender of those messages is an equivocator or has equivocated. They didn't execute the protocol just once, because if they had, then all of the messages they'd make, all the messages signed by the same sender, would have a protocol state transition through the protocol states that are identified by the message. So we can then, if we have weights on the validators, we can count from a protocol state the total weight of the equivocating validators as the sum of the validators such that there exists an equivocation in the protocol state. Because remember that the protocol state is just so far all we know is that it has a set of messages. Because receiving a message corresponds to a protocol state. And actually, we're basically going to tie the knot like this. The protocol states are going to be sets of messages that exhibit not more than some number of Byzantine faults. So any set of messages that it doesn't show too many Byzantine faults is going to be a protocol state. And protocol states are sets of messages, and messages are labeled protocol states, labeled by the validators. And with this kind of construction, we kind of get one of the main properties that we're looking for, right? Which is that as long as there's less than some number of protocol states, as long as there's less than some number of Byzantine faults, then we're going to have a protocol state in common. So basically, when we receive a protocol state, when we receive a message, it corresponds to a protocol state transition as long as it doesn't show us too many Byzantine faults. So if this new message would show us more than T Byzantine faults, then we don't accept it. Otherwise, we will have a state transition to this new set of messages, which includes this new message M. So receiving a protocol state transition is kind of like receiving a message. We go from a set to a superset that exhibits less than some number of faults. And we know that protocol states can kind of be represented as this kind of type of graphical representation where we align the messages with the same label vertically. So basically, I'm going to skip this slide because I'm going to get back to it in a couple more. So basically, this is kind of the kind of main point here, is that two nodes have a common future state if there's not more than some number of Byzantine faults in the union of their states, the union of their views, because the protocol state structure is defined so that the protocol state exists as long as their union has less than some number of faults, and it doesn't exist if they don't have that number of faults. So, well, if we have a common future, so we have a common future basically if and only if the two protocol states have less than some number of, or not more than some number of Byzantine faults. So if there's not more than some number of Byzantine faults, then we have a common future, which was kind of our whole goal to accomplish. And it was kind of interesting because what we did was we said, oh, look, protocol states are sets of messages, and then we found a way to count Byzantine faults, and then we removed all the protocol states that had too many Byzantine faults. And now somehow nodes have common feature states as long as there's less than some number of Byzantine faults. And it kind of is a nebulous and mysterious thing. But we do have the consensus safety proof the way it's supposed to look, which is that if there's not more than some number of Byzantine faults, then nodes only visit states with common futures, which means that they will make consensus safe decisions in the framework given in the first part of the proof. And if there's consensus failure, then that means that nodes didn't have a common future, which means that there must have been more than t Byzantine faults, because there's no other way for nodes not to have a common future. And so we kind of ended up getting pretty much what we wanted without saying anything about the estimator. But we're gonna spend a bit of time trying to understand this protocol state, these protocol states, because it's a weird lattice thing that used to be a lattice, but before it got a whole bunch of points removed. So here's this notion of lost state. A lost state. Let's see. Yeah. So a lost state is a state with which you no longer have a common future state after taking a transition. So if I transition from state 1 to state 2, all the states with which I no longer have a common future state are called lost. Those are the states with which I no longer have consensus safety with by virtue of the invariance in all future states. So whenever I take a state transition, I'm going to lose some states. And those are the ones with which I'm kind of making an irreversible decision, that I can somehow, or like permanently forked off from them in protocol execution. So basically, I'm going to use this little squiggle to denote that they have a common future, symmetric relation, and a little dash to say when they don't. So the lost states from like one state to another are all the states that are have a common future with the first but not the second. And here I'm kind of assuming, actually, I didn't mention it, that sigma prime is a future state of sigma. So let's think about what happens when we receive a single message. Well, in our protocol states, firstly, we can rewrite the definition of lost because we have a common future state if and only if the fault count is less than or equal to t, and we don't have a common future state if and only if the fault count is greater than t. So we can rewrite the definition of lost here to, instead of using common future states, to use the fault count in the protocol state. And then we kind of notice actually that, since these two protocol states here, sigma union sigma double prime and sigma union m union sigma double prime, are only different by one message m here, which is like a single, kind of the assumption here is that this is a single message. Then the Byzantine fault tolerance can only be off by 1, which means that the fault tolerance on the left there has to be exactly t, and the fault tolerance on the right is exactly t plus 1. So basically the stucks. So basically the lost states are the ones which we used to have t Byzantine faults with, but when we added the additional message, we had t plus 1 faults with. And this is actually kind of assuming that all the faults have weight 1. But then this is kind of the idea that somehow the states that are lost when you add a single message, when you take a single protocol state transition, are the ones for which that message is exactly the equivocation that pushes them over the boundary of t faults. And the interesting thing here is that every single message is an equivocation with respect to some other messages. And so every time any node makes a message in the protocol states, they are kind of bifurcating the protocol state in the sense of making it impossible for two protocol states to share a common future. because there always exists a protocol state where that Byzantine fault is the one that kind of pushes it over the edge. And so every time, and so kind of some of the hidden magic that's going on is that every node is able to bifurcate the protocol space through an independent, uncoordinated decision of making a message which kind of it distinguishes its protocol state from all the protocol states in which that message is in equivocation. So that's kind of maybe helps shed a little bit of light as to what's going on here in this protocol state structure that is giving us actually consensus safety. So, because remember, let me do a little recap before we go much further, that the setup is that as long as we have a common feature state, that we will have consensus safety, as long for any estimator, if we decide on invariant stuff, and that we will have a common feature state because protocol states are sets of messages that exhibit less than some number of faults. So we'll have a common feature state as long as there's less than some number of faults, because protocol states are like specifically designed so that they have feature states if and only if there's less than some number of equivocation faults. And so, you can kind of show that like if there's less than some number of faults, then you'll definitely have a common feature state. And if you have a common feature state, that we have consensus safety. And and some of the magic that's going on here is that nodes are not really having to coordinate to bifurcate the protocol space, because every message, whether it's equivocating or not, has states with which it causes to no longer have common features if it's added to one or the other. So now we're going to talk about liveness, which is going to be maybe a little more interesting and give us hopefully more insight into the nature of these protocol states, which are really very minimalistic and say very little about the protocol, but which give us consensus safety anyways. So here's like a recursive, not super well-founded, apparently, definition of eventually, which basically says that, oh look, some property eventually holds of protocol states. If it holds now, or if for any future protocol state, it eventually holds. This basically means that, it either holds now, or any way that we can go into the future, it will also eventually hold, which means that it either holds then, or for any way that it can go into the future, it will eventually hold. And so it's a recursive definition and it says like, and it's parametric in some property that we're saying is going to eventually hold, and some state of the consensus. And there is a closed form for this definition, and it basically says that some property eventually holds if for every protocol execution starting from sigma that is kind of a complete protocol execution or kind of arbitrarily long or terminating, then P will happen at some n, like for some n steps, for some big enough n. Possibly, instead of it being a property that P is going to hold for all future states, sigma, or the current one, it's just going to be that there exists one. And this is the same as the closed form, which basically just says that there exists a common future state, there exists a future state, sigma prime, that holds, or P holds. So we're going to giving some of these definitions in order to build up to the language required to talk about liveness, right? So basically, here's what liveness means, right? Liveness means that we're going to eventually have safety. We're live in some state sigma if eventually we're going to have either safe P at for some future state. For some future state. So this X kind of is like meant to be like the holder for future states of sigma. So eventually the property that we have here is this higher level property that like replaced the protocol states with some placeholder, right? So eventually we either have safety on P or safety on not P, is the same thing as being live on P at state sigma. Martin, yes. So this eventually means for all. So eventually means that for all future states. Oh, so X is like this. So this property P here, this higher level property P, like is parametric in protocol states, and so this X is like the parameter, the like free variable in P. So it just means that eventually there's going to be some future state of sigma that satisfies this. It doesn't mean that they will be satisfied for all future states, but the definition of safety does imply that. The definition of eventually doesn't. All right, eventually just says that eventually you have some property. Safety means that it's for all future states you have some property. This means that like eventually you get to a point where we have this property for all future states of safety on P or not P. Yeah, hi. Imagine. So the question is like, what's eventually from modal logic? It's imagine if it was like necessary for all future protocol states, as opposed to, so there's like we have this notion of before and after, right, of this protocol state, and that's the main difference, right? As opposed to just thinking about does like all possible worlds, we're thinking about all possible future worlds, and that's the main kind of separation there. So a stuckness. So the protocol is said to be be stuck at some P if you don't have eventually safe P or eventually safe not P. There's no not in there. That's a mistake. Okay, well, hopefully this one is better. Refresh my slides. Oh, great. So being not stuck means you'll eventually be at one or the other. I think this is a little bit of a stronger definition than the most updated ones, unfortunately, Nate. But it's okay. Bivalent means that there exists a protocol state transition to safe on P and one that's safe on not P. It's this kind of this property that non-triviality requires, that from some state, we are bivalent. From some initial state, we're bivalent. So FLP impossibility is kind of this result that I'm going to whiteboard up after showing you the outline, which is, I think, a super interesting result in consensus protocols that says that it's impossible for like a deterministic protocol to be safe in live in asynchrony. For us, we're going to be able to show this result for any estimator for in the CBC Casper protocols, any non-trivial estimator. To show that they're basically not necessarily live on asynchrony, because basically we haven't made restrictions about what messages we could receive, except for that they can't show too many Byzantine faults, which means they could be received in any order. So we're going to show in our like asynchronous definition that we don't have liveness, that it's not the case that eventually you have safety for any non-trivial protocol. And here's kind of the outline of the proof. I feel like I dropped something. So basically we're going to do a proof by contradiction. We're going to assume that there is a bivalent protocol state that has no future bivalent protocol state, in order to prove that actually every bivalent protocol state has a future bivalent protocol state. And so if every bivalent protocol state has a future bivalent state, then we can find a trace through the protocol which will not ever terminate and not ever be safe on one value or the other. So we're going to assume that there exists such a bivalent state with no future bivalent state. And then we're going to look at some of the transitions that we have to have, like receiving new latest messages from the different validators. And we're going to pick two of them, which aren't in equivocation. Each of them, like the transition doesn't increase the equivocation count for seeing each of them. Neither are they in equivocation with respect to each other, and such that one of them is locked on P and one of them is locked on not P. We're going to find these transitions, and we're going to use these to show a contradiction. Namely that, it can't be that our initial state was bivalent because we find one that is, or show that one of these guys isn't actually locked. and then that'll show, that'll like kind of finish our proof and show that there must be a future bivalent state. So basically what I'm going to do is I'm going to just try to whiteboard out the piece of the proof here that is kind of missing, and then wrap up my talk and do questions. So basically any protocol state always has some transitions that correspond to receiving new messages from validators, right? At any point, you could receive a message from a validator that says, hey, look, I'm at this protocol state. And actually, for any validator that you can also receive one that isn't an equivocation. So we have at least, for the number of validators, number of possible transitions, and at least the number of validator possible transitions that don't show any new equivocations. Because for every validator, there's going to be a new possible message you can receive from them that doesn't show any equivocations. So we have a number of transitions from any protocol state. We're assuming though that this one is bivalent, which means that some of the future states can go to P, and some of the future states can go to not P. We're assuming that none of its future states are bivalent, which means that all of these future states are locked on P or locked on not P. And so each one of these, so we're going to be able to like split them up somehow to some groups, like mutually exclusive groups, of the ones that are locked on P. So these ones are destined to be safe on P. You can't ever be safe on not P. And these are locked on not P, say. And now what I need to do is I need to pick. So all of these ones I constructed so that they're not themselves increasing the Byzantine fault count. So the Byzantine fault count at any of these states are obviously less than T because we had a transition, less than or equal to T because we had a transition to them, and all the protocol states have less than or equal to T Byzantine faults. But also I'm saying like, oh, this didn't lead to an increase. So if this was T Byzantine faults, then this couldn't have been less than T. So these guys are none of these show equivocations. Now I need to pick two of them. One that's locked on P and one that's not locked on not P that aren't an equivocation. Well, in the kind of worst case, well, if as soon as I pick one here, if I have a choice between two different validators here, I can pick, as long as I pick one that's a different validator, then it's not going to be an equivocation. And so as long as I have more than one choice in every option, then I'm going to be able to pick two which are not an equivocation with respect to each other because they're sent by different validators. So let's say that like, because so in the worst case we could have no choice in one of them and just have one possible choice. Then we just have to find one of them in the other that has a different validator. And so we can just, and if we find one that has the same validator, we can just pick a new one. So if these two guys have different validators, we call this message M1 and this message M2. Then the claim is that, oh, this protocol state here also exists. And this protocol state transition here corresponds to receiving message M2. This protocol state transition here corresponds to receiving message M1. And the kind of result is, look, okay, well, this has T or less Byzantine faults. M1 didn't increase the Byzantine fault count from here, but this one doesn't differ from this guy except for by the presence of M2, which is not a Byzantine fault with respect to M1 by construction. And so this one also can't increase the Byzantine fault count. And any protocol state that doesn't have more than T faults is a protocol state that exists. And similarly here, this transition doesn't increase the number of Byzantine faults, which means that these two protocol states actually share a common future protocol state. But that means that they can't actually be locked on P and locked on not P as assumed, or as was corollary to the fact that we're assuming that there are no bivalent states, because they obviously share a common future state, and if they're locked on mutually exclusive outcomes, they obviously don't share a common future state. So we show this contradiction, and therefore, like our initial assumption that there was a state that there was a bivalent state that didn't have a bivalent future state was false. And basically we did it by carefully choosing the protocol state transition so as to not show any Byzantine faults. Because as long as we don't show more Byzantine faults, then we're not going to have, then we are going to have a common future protocol state. And in this case, that meant that two outcomes that were supposedly locked and mutually exclusive outcomes weren't, because they had a common future state. So that's kind of the proof. It basically shows that every protocol state has every bivalent protocol state has a bivalent future protocol state, which entails this FLP impossibility result that we can't have liveness in asynchrony. Because in asynchrony, any messages could arrive in any order, and we could potentially be stuck in this bivalent loop, or in this bivalent execution. So here's like some of the cool things that we can do with these protocol states in the state transition picture. We can think about liveness totally independently of safety, actually, because our protocol spec so far guarantees safety, but it doesn't tell us anything about when validators send messages or when they receive messages. It's very, very minimalistic. All we know about is the protocol states that the validator can transition to in terms of like the sets of messages that they could possibly receive. We were able to talk about proof consensus safety and FLP without talking about the estimator at all, without talking about actually what is the thing that we're coming to consensus on. And so, this lets us pretty quickly iterate and build different consensus protocols, because we don't need to change the protocol state very much, because they all have this property that, like, look, you can count Byzantine faults, and that protocol states don't have too many of them, and that any protocol state that doesn't have too many of them is this protocol state. We have an extra protocol fault tolerance threshold. I didn't ever mention, like, oh, this is the number of Byzantine faults that we can tolerate. That number T of less than that, like, we need to, that like you decide, like, sorry, then that number T that we use to decide which protocol states, which sets of messages are protocol states, is up to the individual clients. And if two clients run with two different protocol fault tolerance thresholds, then they have consensus safety as long as the least of their fault tolerance thresholds isn't violated by more than that number of faults. And basically, so like the pitch here is kind of that we get asynchronous consensus safety almost for free without saying almost anything about the protocol, other than providing a way to detect Byzantine faults and a restriction for when do we make decisions to be only when they're safe, in this sense of invariant over all future protocol states. So we have some docs, we have some code, and we have some more and more like forums for people to chat about CBC Casper, and try to discover more about this mathematical structure, and try to understand consensus protocols and how to build actually really complicated consensus protocols that don't entail nodes making the same decisions on everything, but are potentially more scalable. So thanks so much. Really appreciate it. Happy to be here. Got some time for questions, I guess. Oh yeah, we got some cool slides actually.
Hi. I was wondering if there's a minimum number to the validator set in your FLP proof. It sounds like there is.
No, there isn't.
So.
You mean if there's too few validators, the proof won't work?
Yes.
I believe that number is 2, but it might be 3. I'm investigating.
Cool, thanks.
3 is definitely going to do it, but 2 I'm not sure about. With 1, you can get liveness really easily. We have some graphical representations here. I'm trying to. So this is like a binary consensus protocol running these protocol states with an estimator that maps these things to 0 and 1, and an estimator from which we have like a safety oracle. And the color of the node represents the fault tolerance with which that node has been able to, assign the fault tolerance of that particular estimate. The cool thing about this, like as I mentioned, is that we didn't make any restrictions about who sees what messages when, so we can make all sorts of different message arrival orders work, and they all are understood in the same way in terms of the distributed consensus proofs. We have this consensus on an integer here with median. Turns out 78 was the winner. Now we got the same thing again, and here we have the nodes different, but with rounds instead of this more random message format. This is the blockchain consensus that we have a prototype of. It uses an estimator as a fork-choice rule, and it's given in the estimator of our view here is given in red, and of the individual validator's latest messages are given in blue. And the color of these blocks represents the fault tolerance, and you can kind of see the fault tolerance of any block increasing actually kind of quickly after additional messages. But the cool thing about all these protocols is they all satisfy the same safety proof, and they're really indistinguishable from the point of view of the safety proof, even though the nature of the consensus protocol from the point of view of the user experience and the service being provided is quite different. We can get really asymptotically optimal network overhead numbers with, we can explore a lot of trade-offs in the overhead, latency, number of validators trade-off for consensus protocols. So in this, you kind of see asynchronous BFT consensus happening with the overhead of Nakamoto consensus. Cool, that's all my little demos, I think. Question?
Yeah, I was wondering if you could talk a little bit about how validators would choose optimal T, where
optimal. Oh yeah, so that's a good question. So I mean, basically, there's a trade-off where like the lower fault tolerance threshold you use, the faster you make decisions, but the more likely you are to make inconsistent decisions because like the amount of faults that you tolerate are less. If you choose a higher fault tolerance threshold, the probability that your transaction will end up being in conflict with what someone else believes on the network is much lower, presumably, because presumably higher fault counts are less likely than lower fault counts. And so basically, you kind of like today you choose between waiting 1 confirmation or 6 confirmations in Bitcoin. People will choose between, there will be like norms that arise about like what number of faults you wait for. Like, do I want to wait for this coffee to tolerate more than 1 Byzantine fault? Like maybe not. But for the Lambo, you gotta wait for like a good like 50% fault tolerance or something. Who knows?
Hey, can modifying your fault tolerance result in equivocation?
No, equivocation just means not following. Basically, it means not evidencing a single-threaded execution to the protocol. So, the fault tolerance threshold isn't even part of the protocol, really, just a parameter as far as the protocol is concerned. And so, like actually changing it isn't even recognized as a protocol state transition. If one day it does, then don't worry, we'll make sure that you can't accidentally equivocate by changing your fault tolerance threshold.
Do you see any future conflict in applying this within namespaces and regions and having to either come to a consensus within a namespace before it moves on? Or is this going to not even be affected by those sort of
No, I mean, it should be completely orthogonal. Like, just like we can replicate blockchains or sharded blockchains, we should be able to replicate this namespace structure. It's like another thing to replicate as far as this construction is concerned. So yeah, it should be completely independent. Although, we also have the ability to get fancy. And so it might not look a lot like what it does now, but definitely you'll always have like a sender and a fingerprint of the protocol state from which they sent it. Otherwise, you're not going to be able to do Byzantine fault detection and take advantage of the safety proof. And I think like if you want, and I think taking advantage of this construction will be helpful for iterating without having to reason about the consensus proof over and over again. Go ahead.
So what, if any, have you done on theoretical and or actually tested kind of performance metrics at various ranges of t and
Well, I mean, like
transactions per second
theoretically, we're able to explore like a really huge area of trade-offs, and so like we can reach like theoretical optimality in terms of minimizing the overhead of the protocol. Not necessarily in terms of minimizing latency to finality, because that takes kind of cryptography to do that. And we have some prototypes, but I don't think we've gotten like testing really, except for in prototype. But soon.
Thank you.
So, if there's no more questions, should we call it 5 minutes early?
All right. I've got a couple of announcements just to sort of get you guys directed.
Wait, let them clap for me first now.
Oh, I'm sorry. Nice job, Vlad.
Yeah, my pleasure.
My recruiters chided me for not mentioning that if you're interested in working for us, email your resume to jobs@pyrofx.net, right? So then you can work on the Archain project if you're interested in Scala.